the talk is a lot about IoT devices. So you probably heard a lot about IoT devices. So many years ago when I started to tell people, oh, my research area is IoT devices, they would say, But now when people say, I'm guessing they are thinking, oh, buzzword. She's working in some area in a buzzword. Anyhow, so there's a lot of prediction on IoT, how many devices there will be in the future. So this is one of them. It's predicted by 2020, there's like 50 billion devices. You may think, is that possible? So actually, if you look around, things are already happening. So this is in China. There's about 200 million surveillance cameras installed in major city. And with the prediction, probably there will be close to 700 million surveillance cameras installed by 2020. And so with this camera and also the facial recognition technology and a lot of AI technology, actually we can track people. Of course, the intention was to find criminal, right? So like in the city where I work now, Hangzhou, if there's any criminal event happen, then within minutes we can find where the person is. We can track him down on the major highway, including. So now we're almost close to the IoT era, right? So the thing with IoT is we know the best stuff. You probably heard this incident. You heard about phishing attack. But now there's this fish tank in Las Vegas. It's connected to internet, of course, like the keynote speaker said, with potato hands attached with wireless communication. It's connected to internet. At the same time, it's connected to the internal network of this casino. So hacker managed to steal data. And so this is only information leak, right? Leakage. But if you think about IoT, the thing with IoT is it's a network of physical objects, and they are connecting to the real world. And so you probably from this picture, you already know it's Stuxnet. We heard a lot. With this worm, some hacker, I'll keep it anonymous, some hacker managed to destroy the centrifuge in Iran, right? So delayed Iran's nuclear program for at least by 2 years. And there's black energy. It destroyed, not destroyed, it caused big power outage at Ukraine. So these are all examples showing that in the IoT world, the breach actually can affect the real world. Now, the question here is, we have internet for decades. So what's new with IoT? Of course, there's a lot of problem from internet kind of automatically migrate to IoT field. So we try to dig what's new. If you look at the smart devices, a typical IoT devices, it has the capability of sensing, computing, communicating, and control. So therefore, for each devices, it may have all 4 components, right? Sensors, MCU, communication units, and actuator. Now, if you look at this, and if you think about it, so the message I try to give here is it's actually time to look at the physics of cybersecurity. Why? There are 2 aspects. First, if you look at these devices, it's actually closely, it's physics in loop, the physical world in the loop. The sensor sense environment and processor do some calculation based on application, the actuator control the physical world. So we're interacting with the physical world. Now the second thing is, if you look at these devices themselves, they are physical devices, right? So besides what we are familiar with, the digital binary information, what's underlying, they're actually analog signals. So if you look at MCU, you probably heard about row hammer, right? That's a great example showing that with memory, it's not binary. It's analog. So there can be leakage between memory cell and causing information change on the digital world. So same thing happened with sensors and actuator. So sensor, it's not just a device that output binary sequence. It's actually there are a lot of electrical component connecting from the physical world to the digital world. So I will explain it a little bit. So in this talk, I'm just going to focus on sensor security. So sensors are everywhere. If you have a smartphone, there's at least 14 sensors on your smartphone. Now, if you look at cars, modern cars have between 60 to 100 sensors. And in the future, there might be 200. If you look at critical infrastructure, power grids, or small, like medical devices, they all have sensors. So what about these sensors? So now I want to point out that we're looking at sensor security. And we're looking at whether the integrity of sensor is what we believe as a programmer or as a hardware designer. So the reason why we care for that is you probably heard a lot of accidental interferences, right? This is a picture from New York Times. So what happened is that in this household, every time the owner places their cell phone on the oven, every time the oven rings, the oven will automatically turn on and start to bake. So what happened? It's actually the cellular signal is interfering with the circuit inside the oven. And then the control part will think, oh, it's a command saying turn it on. So this is just a great example showing that you don't have to get inside sensors from outside with a lot of different interference. You may be able to make these devices behave unusually. If you don't believe I gave you another example. So sensors are their proxy of reality. So what I display on this figure is actually a thermocouple. So we know how thermocouple work, right? It converts temperature into binaries. And the thermocouple typically have two wires. When these two wires are under different temperature, and then the voltage output from these two wires will change. So this is, if you look at the room temperature, it's only like 73 Fahrenheit. The green thing is actually an antenna. So we're pumping out EMI, which is picked up by the thermocouple. Great antenna, right? Any conductor that's exposed to EMI is basically an antenna. So we make this thermocouple output the temperature probably, I don't know whether there's some place on the earth have that temperature. Anyhow, this is just one example showing you shouldn't trust what sensor tells you based on the existing design. So then now when sensor goes wrong, how will the system behave? Let me give you one example. Well, Tesla, unfortunately, we always pick Tesla because they have the closest autonomous driving system on the commercial market. So you heard about Autopilot. The car can drive itself, and also there is this summon feature. So the car actually can park for you. You don't have to be physically in the car, and the car can park itself. Of course, all these capability relies on sensors, especially the obstacle detection sensors. And for autonomous driving, self-driving, the most important thing is to make the right driving decision, when to stop and when you shouldn't stop, right? So I'm going to just show you a small video that we made. So in this video, this white car is a Tesla. It's in the summon mode. So I show first when we don't launch the attack, and then we start to fool the obstacle sensor. So let me just play it. So now our attacking tool, basically the bar behind the student, very brave student, is turned off. And now Tesla is in its regular summon mode. So it refused to back because it detects there's a human standing behind. Now we turn on the power supply to this interferer. And then we reboot the car. We use the remote to turn the car's engine off and turn it on again. Now this time, actually the obstacle sensors are not doing its job. It didn't detect there's a human standing behind. So this is just an example showing that when sensor goes wrong, with existing system, how they will behave. So just a little bit side story. So we are actually attacking the acoustic sensors. And there's actually two types of acoustic sensors on the market. One is used in the car, the other is used for distance, like measurement. So we got both, and we launched the same attack to these two types of sensors. You may imagine that you would think the car sensors is more secure and safer, right? It turned out our attack will not work to the cheap distance measurement sensor, but works almost on all the sensors that's used on the car. That's because the designer was thinking smartly. They add some smart feature called noise suppression. And so because of that feature, so we were able to hide obstacles. So this is just one more example showing that a lot of engineers, they just don't think security during the design phase, and then what it will lead to. Okay, anyhow, so sensor security, cool topic, but I did encounter people, they will think, where do I start? Sensors are so different, so how to do research in sensors? So in the rest of the talk, I'll try to give you some flavor on the following question. So is that a genetic sensor model? Because sensors are so different. Do I have to learn each sensor, or they have some similarity? The second is, can we affect the integrity sensors from outside? Actually, I already showed you one example, but is that true for all sensors? And what is the status quo of sensors in terms of programming and system design? So what is the abstraction of sensor? Yesterday, we heard that abstraction is actually not the good thing in terms of security. So let's revisit the topic. And in the end, so how to protect the integrity of sensors. So let me start with what is inside a sensor module, and can we find a common thing between all different types of sensors, the accelerometers, gyroscope, and obstacle detection. So anyhow, so sensor is actually a transducer, right? From this picture, the goal of sensor is to sense the physical signal and turn it into some electrical signal so that the operating system and other system can understand. Or in some sense, you can think sensor as a energy transducer. So it convert, for instance, if you think antenna, it's actually a sensor as well. It convert electromagnetic signal into binary, the communication content. And some sensor convert mechanical energy into electric. Radiant, magnetic, thermal, and chemistry, all these different signals into, in the end, the electrical signal. So I'm going to just give you a little bit on one type, piezoelectric sensor. You probably heard about it. So with this sensor, it can convert pressure, acceleration, temperature, strain, or force into voltage change. So as the figure illustrates, when you squeeze that sensor, it output voltage. So actually, for speakers, it also uses piezoelectric sensor, but it's used the opposite. So when you apply voltage to this piezoelectric sensor, it will change into a vibration and producing sound. So anyhow, this is the sensing module. I mean, the sensor, but inside a sensor module, sensor itself is not enough because the sensor still output analog signal. And after the analog signal, the sensor convert, there's a sequence of processing module, which includes amplifier, which increase the amplitude of the measured signal. And there's low pass filter, will remove noise, supposedly. And also there's AD converter, analog to digital converter. And in the end, we get sequence of binary. So this is actually a pretty common model for most of sensors. Most of the difference coming to the first part, so how sensor convert physical signal into the electrical one. Now, let's look at the thread model. So we can think about each blue box, either it's an amplifier sensor as a single module. So each module actually take an input and output a signal. So how can we manipulate that module? There's actually two entrance points. One is we can add interference input like noise on top of what it's sensing. And the other is we can modify the module itself. So for instance, I can change the temperature or I can put sensor under some weird exposure of other signals, and then or humidity, and then the sensor may behave differently. So in the end, what the sensor output will be the combination of what it's supposed to measure versus what's our malicious, input. Okay, so how many different type of malicious input we can get? So there's actually a lot of malicious signal. We've tried IF, acoustic. We haven't tried light, magnet, and heat yet, but at least for the IF signal, it's doable. So actually, we managed to inject sound into a recorder. So in the room, there's like it's quiet, but we managed to inject music using IF. So if you're interested, the paper's title is Ghost Talk, right? In Halloween, you can play that with your friend. Anyhow, so, okay, enough talk on the general thing. So I'd like to give you like a few case study on what we've done. This is, the first piece of work is Dolphin attack. That's what Kevin mentioned. So it's reported in various media. So basically we can inject hidden command. So before I start, let me just quickly go through how the modern speech recognition system work. So first, we have a voice command coming as a mechanical wave, and the microphone will convert it into electrical signal. The digitized electric signal will be input into the speech recognition system, and then the speech recognition system will output text. Depending on which system, the voice assistant is connected to, the command will be passed to Echo, car, watch, your phone, etc., and then execute command. So apparently this voice assistant has become really quite a hot topic. I know there's already 2 papers on this topic in USENIX. So most of their work are looking at the speech recognition part or the system part. So they try to find adversary machine example to fool the system. So what we look at is the sensor itself. So a microphone is basically a sensor. So we want to inject a sound command you cannot hear by leveraging the vulnerability inside microphone. So we want to fool the sensor. So let me first show you the video, what we managed to do. So in this video, the black iPhone is actually the victim device we try to attack. And then the white one is actually the one that we try to send command. So there's 2 parts. The first part is the normal use, what you're familiar with. And the second part is actually we try to send inaudible voice command to activate the phone and make a phone call. Okay, I'm going to just play it.
Hey Siri, call 1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
This is normal use. Right, so now we'll lock the phone. Oh, by the way, the silver box is actually an ultrasound speaker. So now we lock the phone and then connect the white phone to the ultrasound speaker. And you didn't hear anything, right? But the black phone started to make phone calls. So what happened? Let me just quickly go through the acoustic part. So we know if you look at the frequency for this acoustic dimension, then from low to high, it's like a low frequency to high frequency. Different animals can hear different sound. And Dolphin is right there. Our attack is called Dolphin attack. Anyhow, we can simplify this category into like a 3-story building, right? In the basement is the info sound, and then the output sound is on the first floor, and then the second floor is the ultrasound. So as a human, we only live in the first floor. But with microphone, it actually can cover a broader range than the first floor. So what happened is that in normal case, we think the voice assistant work on the first floor and everything happened in the range that we can detect. For our attack, what we managed to do is we managed to send signal from the second floor, although there's nothing happened on the first floor, because there is a vulnerability with the microphone. So somehow the signal will down convert to the first floor and then picked up by the voice controllable system. So this is like a high-level introduction that I try to explain to my grandma. But as a lot of people here, probably you won't feel comfortable without seeing a FFT plot, right, spectrum. So let me just go through what happened on the frequency zone. So first we send an ultrasound. The ultrasound is actually modulated onto a carrier of, let's say, 25 kilohertz. Now in this plot, the blue line is actually the wall between where a human can hear and where we can't. So once the signal goes through a microphone, because the microphone has this nonlinearity, and which means that the signal can actually change. I mean, the frequency can change. So what happened is that the baseband on the carrier will be somehow down converted to its original baseband. Now we have this red signal in the audible range. And then after amplification, nothing happened. And after low-pass filter, the low-pass filter actually will remove the ultrasound part. And then once it's passing through ADC, then the signal will be picked up by the speech recognition system. So someone may wonder why we have to use like ultrasound, because a human doesn't hear high frequency like 19 kilohertz, 18 kilohertz. We actually tried that. So interestingly, if we modulate signal onto 19 or 18, because the low-pass filter will not filter out the signal in the 19s, the speech recognition system does not recognize the command we inject. So, but once we are in the ultrasound zone, the low-pass filter helped us and make our attack possible. Okay. Anyhow, so I want to show you a few more movies. I haven't shown this to the public yet. This is what we've done lately. So in the video you just see, it seems like the attack distance is really close, right? And we have to use professional ultrasound speaker. But in this case, we only use the transducer that costs $1 per piece, and we like put 40 of them together and put them on a tripod. So we managed to launch the attack from 10 meters. So this is asking for weather. So it's where I live, Hangzhou. And then this is in the hallway. It's actually, the tripod is at 20 meters away. So that's the distance of the hallway. So maybe we should try in the open space, and then there might be a larger range. So I just want to say a little bit about the transmitter. So there's other paper may say that if you play with one sound source, then the nonlinearity of the speaker will make the sound audible, right? From what we have here, we didn't hear sound. So there's actually differences between paper. Why? It's because they didn't pick the right speaker. So their speaker has nonlinearity, but that doesn't mean all speaker has it. So anyhow, so if you are still not satisfied with the distance, we can do something like a remote attack. Here's the setup. So you can have a commodity speaker, doesn't have to be ultrasound speaker, connect to a computer. As you visit a website, there might be a hidden ultrasound clip in the website. When the clip played out through the speaker you're connected to, you may not notice it, but it may inject signal to the smart devices around it. So I'm going to just quickly play this video where we try to let this iWatch to do FaceTime in a market using a commodity speaker. Oh, what did I do? So again, the white one is injecting signal. So you see the iWatch start to FaceTime, but you didn't hear anything. It's in a loud market So that just illustrates if there's a clip in the website, maybe that's possible. Okay, so that's, okay, I probably spent too much time on that. I'm going to speed up a little bit and talk about 2 more case studies. This is the joint work done with Kevin. It's on MEMS sensor. So with MEMS sensor, in your smartphone, there's a lot of MEMS sensor, and accelerometer, gyroscope, they're all MEMS sensor. And they're not only used in smartphone, they're used in airbag and medical devices as well. So how does this accelerometer work? Let me just quickly go through it. So if you look at the left figure, there's like 2 electrode mounting on this MEMS. There's this fixed one, and there's this movable one. The sensing mass is like attached to the attached through a spring to the sensor. So when this MEMS sensor is under acceleration, because there's displacement on this sensing mass, the capacitance between those 2 electrodes change, and thus we can measure the change and convert it into voltage. So that's the normal use. But with any mechanical sensor, we know there's resonance, right? So if we shake the sensor with sound, if we hit the resonant frequency, then what happens is that the sensing mass will shake. So the output of this sensor will be the combination between the real acceleration and the vibration caused by the sound, right? So simple enough. So, but you think the designer probably should have learned that, because it's like in the primary school, your physics teacher already told you there's resonant frequency, right? So you would imagine that with low-pass filter, it probably will remove the sound because the sound frequency is much higher than acceleration. So then you may imagine the output of acceleration under different sound should be 0, should be flat. So what's the reality? These are the 40 accelerometers we tested. So for each spike, so the x-axis is the frequency, and the y-axis is the output. The blue one is the mean, and the red one is the standard deviation. So for each spike, it means at that frequency, we manage to let the sensor output some value while the sensor is actually stationary, laying on the table only. So for instance, with this sensor, the sensor is vulnerable to the sound under 5 kilohertz. Also, it's vulnerable to frequency at maybe 2 kilohertz. So I'm going to just skip the details, but because I like to tell you the next thing. So let me just say, with sensors, if we just play sound, you think at most we can launch DOS attack, right? We let the sensor malfunction, but we can actually do more than that. We can control the output of sensor. How fine we can control? This is a Fitbit. So we played a sinusoid sound to the Fitbit, and the Fitbit will think it's under a walking human being. So I'm going to just play it. So the Fitbit is inside this DIY soundproof box, and the Fitbit is paired with phone. So you will hear a little bit unpleasant high pitch. That's actually our interference sound. And we use a signal. So this is 11 kilohertz. That's the signal we send. If you look at the step, it's increasing, right, gradually. So if you were in a competition, how many steps you can do every day? We tried like 20 hours, and we managed to have 80,000. So if you want to win some free points, just read our paper and then play it through your phone. Anyhow, so what I want to come into is actually another piece of work that's been come out this year at Oakland. It's called hard drive. Again, this is the collaboration with work with Kevin. So let me start with the news. You probably heard this file drill knockdown ING Bank data center. So it's like in 2016, because of the loud fire alarm, the whole data center of this bank was offline for 10 hours, and they didn't know why. Well, actually, we think it's probably the hard drive. So why? If you think about hard drive, this is like an internal look of a hard drive. It's like a record player, right? We have the actuator arm, we have the read-write head floating on top of a platter. So when the arm is on the side, then it's stopped. When the arm is on this platter, then it's working. So if you think about a hard drive, it's actually a kind of a CPS or IoT device because there's a sensor in it, and there's a processor, and there's actuator. The read and write head is actually an actuator. So it's actually a very nice example to illustrate what can go wrong in a bigger system. At the same time, because it's hard drive, it's there for decades, and operating system seems to know how to interact with hard drive. And we want to figure out what's going on with that file drill. So the first thing we did is we drill a hole of this hard drive. So you see the red box, it's a window that and then you can see the head moving back and forth. So when we play this music, you are crazy. Every time when the sound goes to you see the arm actually parked. So the hard drive stopped reading. So I'm gonna play the video.
I remember when I lost my mind. There was something so pleasant about that place. Even your emotions had an echo in so much space.
So every time the sound plays A, the arm just stopped. So then, which means that if you're reading something from the hard drive, you're trying to read that, then it's not possible. The read was delayed. So there's actually all sorts of different story. There's this guy, every time when he hear one music, his computer crashed. So he tried to figure out the reason for the whole week. He listened to the song for the whole week. Eventually he figured, oh, it's that pitch causing the hard drive to do something funny. Anyhow, so let me move on. So you may ask, so what is the threat model? Who are going to play file drill in the database? Right? If you think about modern computers, there's built-in speakers, or there's a tiny speakers like what displayed here, that big transducer. It can be hidden somewhere, can affect your hard drive. So now, how much can we do? Okay, so this is actually the 32 kilohertz transducer that we use in our later video. So first of all, we use Cosmo to simulate a hard drive and try to figure out what went wrong on the sound. So this is under 5 kilohertz resonant frequency, the displacement of hard drive. So we notice that the platter and the read-write head both have displacement. This is one aspect. The other aspect is, inside hard drive there's a shock sensor. It's designed to protect the hard drive, right? If the hard drive is in a free drop, then the head will park. So that protect the hard drive. So what we managed to do is, so in this computer, we hide a transducer under this hard drive, and then we were doing a large file copying. So what you see here is the progress bar. So I'm going to just play it. So, so first, this is the throughput. Once we start to play the ultrasound, you won't hear it. And the throughput actually will drop to, so it's actually dropped to 0 already. And after a few minutes, we heard that the clicking sound inside the hard drive. So the head is probably confused doing something because we're using ultrasound. Oh, okay. Yeah, it's in the end, the whole computer just crashed, and it going to this black screen, not necessarily blue. So what happened is that the shock sensor, we found the resonant frequency of the shock sensor, similar phenomena as the accelerometers. And then the shock sensor will think there's acceleration and instruct the hard drive to park its head. And then the operating system apparently didn't expect that will happen. So the operating system think the hard drive is broken. So then the kernel get into this panic mode, and so this is what happened. And we also did one more case study. We found one surveillance camera. So it's a 4-channel surveillance camera, and the video was streamed to a hard drive. So you probably can guess what will happen. So what happened is we played so this is actually a clock. So you will see as the clock ticking, certainly there's a jump between, I think it's 11 seconds. Yeah, so you see a jump from 11 seconds to 1 minute and 32. It's because the hard drive is under acoustic attack, and the system can't there's only that amount of cache. The system can't dump the cache into the system. So what happened is that the system will just throw away all these videos. So in the physics of this world, if you want to sneak into a building without being caught, if you don't want to leave anything in the log file, I think you should go physical, right? With acoustic weapon, I probably shouldn't use that word. You can just sneak in without leaving any trace. So anyhow, the 80 seconds of videos are missing. Okay, so that's just a few examples. I just want to give you some flavor. What can go wrong with sensors? Okay, I only have like 1 minute left. So perfect. So this is the conclusion. Oh, I have 7 minutes. So okay. I probably gone too fast. Okay, then I can stay on this slide for a little bit. Okay, so I have a clock here. It seems like it's ticking faster. Someone may have launched attack to my computer. Anyhow, so we talk a lot about the risk, what can go wrong, and we talk about how does the system behave. So I think essentially the system. Because of so first of all, there's risk from actually different aspects. So I only showed acoustic, but we've done RF. So we can use RF to inject signal into sensors, which make the sensor output anomaly data, or the data doesn't reflect reality. With the obstacle detection sensor, they're actually active sensor. They're sending out probing signal and then make measurement based on the echo. So with all these type of sensors, there's ways we can change its output without getting inside it. So I think it's important for software designer, hardware designer to understand there's this risk. Because existing system, they probably just assume sensor either malfunction, produce a reading out of range, or work properly, right? But the example I show is that actually that's not the case. So now looking forward, we have solutions for each of the attack we have. But if we want to give a general solution, so for each system, the defense are slightly different. So for instance, with the Dolphin attack, injecting inaudible voice command, our solution is to use some machine learning technology to detect the signal on the microphone output, because the signal between audible command and Dolphin attack injector command, they're different at high frequency, right? But that's very specific to microphone and to speech recognition system. If we want to give a general solution, I would say first, microprocessors should not blindly trust sensors, and it's probably better for the sensor designer to give additional information to the system instead of just, here's the data, good luck, bye, right? The sensor actually can collect a lot more information. So for instance, the obstacle detection sensor, the ultrasound sensor, it actually can measure what is the ambient acoustic signal level. If it's higher than normal, then I shouldn't trust the reading I output, right? So if the sensor can rethink about the API it provides to the system, and then the software may be able to do some intelligent decision based on how much I should trust these sensors. So, there's actually other work I skipped. I thought I will run out of time. If you're interested, you're welcome to visit our web homepage. And we are hiring all level, tenure position, postdoc, summer interns. If you're interested, shoot me an email. Okay, so with that, ready for question?
Thanks, Wenyuan. So we have a few moments for questions. You can line up at the blank mic and just speak into the ultrasonic. No, I have a mic in my hands. Just state your name and affiliation, please.
Chaim Shnor, Intel. If you look for a general solution, would sensor redundancy with diverse sensors, so they don't respond the same, not the same type, something else, would be a more general advice that would probably be more expensive, but work?
Yeah, so sensor diversity and sensor redundancy definitely can help. But in the end, that's like the arm racing, right? Now you have two types of sensor, then I need to launch an attack that can affect both sensor at the same time. Yeah, so that's a solution, but we want to have different solution to cover the ground.
Hi, I'm Peng Cheng. Thank you for your talk. I'm from Lancaster University in UK. So I basically followed your work and also the work you mentioned, the first backdoor paper, and then your Dolphin attack, and also that the same team did the backdoor. They also published a paper in NDSI, that one you mentioned. So to me, the storyline is like this. First, in the backdoor paper, they tried to also use ultrasound acoustic signal, but because they didn't aim at smart home speaker, so they just did the frequency modulation to hide the command. And then when the microphone receives the signal, they can use another application to decode it. And then in your Dolphin attack, you basically aim at smart home speaker or any voice the voice assistant, and then basically you use the amplitude modulation, because then the nonlinearity of the microphone can just convert the baseband signal. Yeah, and so then NDSI work, they said basically because the nonlinearity of the speaker, if you use the AM, you can hear the sound. But you just mentioned because they chose the wrong speakers. Maybe I'm not sure about this part, but I need to investigate a little bit. And my question is, have you tried just don't use this? The specified equipment like the ultrasound speaker? Did you try just use the off-the-shelf smartphone, the speakers on it, to try to do the Dolphin attack?
So we do have a portable setup to use smartphone, but we don't use the speaker on the smartphone, because the speaker on the smartphone, they're MEM speaker. They're very special, and the transducer I showed that the silver cylinder in the PPT actually is the speaker that doesn't have that much nonlinearity. So with the one on the smartphone, yes, they do. So yeah, there's device dependency experiment. So that's why there's differences.
So we've got about 45 seconds left. So two very quick questions.
Okay, I'm Shenan Liu from USTC, an undergraduate. So my question is that how fine-grained your hard drive attack can be, since we all know that the file systems are written into the hard drives, and can you even locate certain sectors to mess up with the file system? Yeah.
Not yet. That's a good idea, but right now we don't have any feedback from the hard drive, so we don't know where the head is. So therefore, it's difficult to predict where it is.
The last question.
I'm Jamie Davis from Virginia Tech. I'm wondering, at some point your work says we shouldn't trust what our sensors are hearing from the real world. Some of your attacks are intended to hide from humans, but some of them are intended to pretend the world is different from the way it actually is. Would any of your attacks fool a human, or are they just fooling our devices?
So our ultimate goal is to fool devices, but at the same time, speech recognition is like different, special, right? Because there's always human around. So a fooling device itself is not enough. So on the way, we try to make it's unnoticeable to human. So that's the logic.
Okay, well, let's thank Professor Xu. Thanks.